The electrical work, which means the spontaneous reaction, chemical reaction, produce current and voltage. And the voltage we use the reduction half minus oxidation half to calculate. That voltage is actually a force to push electrons. And the voltage or cell potential, it is a symbol, it is an indicator of how strong the force for the source, electrical source, to push electrons, to do work. So just kind of give you some common examples of voltage. Our alkali battery is 1.5 volts. And the lead acid battery is a 6-cell stacked together. So it's the 2 times 6, 12, around 12 volts. The current, the AC power in our household typically is 110, 120 volts, 110 volts. That's AC power. And if you go to some power line, if you go to the more suburban area, rural area, you see the high power, high electric tower with the long cables, miles and miles. Those are very high voltage, hundreds of thousands of volts. So each one shows you how much force they push electrons. Those voltage times the number of electrons, it gives us the work done by the electricity. So the spontaneous reaction, free energy change, the standard free energy change, and the cell potential, there's connection, okay? The connection is, use this equation. Standard free energy change equals negative of the number of electrons in this reaction. This N is the number of electrons in moles. Faraday's is constant. This Faraday's constant, later we'll find out it is basically same value as a ratio between the Coulomb, which is counting how many electrons, and the mole is a ratio between mole and Coulomb. We'll see that later, which is 96,500. So when you have a number of electrons times Faraday's constant times the cell potential, that'll give you the free energy change for the reaction. And we have negative in the front because the cell potential should be positive. If cell potential is positive, the delta G will be negative. And so this equation, since we learned about the free energy change and the equilibrium constant, we learned that equation before, just last week. Free energy change and the equilibrium constant. Okay. So that will give us 2 equations combined together. The K, be careful, the K is actually a Kp. So combine this equation and the voltage and free energy equation. We have the cell potential proportional to the natural log of the equilibrium constant K. The R is 8.314, temperature is Kelvin in kelvins, and the number of mole of electrons, and the Faraday's, that's a Faraday's constant. So this is the universal equation for any temperature. We have this equation. If you use the room temperature, the standard temperature, 25 degrees and or 298 Kelvin, we will have a further equation. Replace T and replace, instead of using natural log, now we use log of 10. We have this equation. In our test, you'll be given, I believe, the left-hand equation, which is because more universal. So you can see the redox reaction, the standard reduction, the standard cell potential, it is related to the equilibrium constant for the reaction. This is amazing, because the last chapter when we discussed about free energy, we find out there's a connection between the equilibrium constant and the free energy change. Now, because free energy change relates to the cell potential, we can see the cell potential relate to the equilibrium constant. When you have a very large equilibrium constant, then you would have a fairly high cell voltage, standard cell voltage. And so that's how the energy and the equilibrium constant and the cell potential all tied in together. So this shows you all the connection among these three quantities: equilibrium constant, free energy change, cell potential. And we learned from the last chapter, standard free energy change is a negative, meaning lose the standard free energy. The reaction is spontaneous, which if it's negative, which means the product's favored by local decay. So the spontaneous, not spontaneous, rigorously speaking, it actually means if this equilibrium favors the reactant or product. When you have a negative free energy change, which means the product is favored in the equilibrium. And the cell potential for the redox reactions, the cell potential is a positive, and that's spontaneous reaction. And when the change is zero, is the cell potential zero. Cell potential zero, which means the redox reaction end. No more reactions. This is equivalent to the when the cell is dead, when the battery is dead, complete no voltage. That's because all the reactant being consumed reach equilibrium with the product. And so that equation we can see from the free energy change and cell potential, you have a N is number of electrons transferred. How to find the number of electrons transferred? There are actually two ways. One way is to use a half reaction method, balance the reaction, and then the least common multiple of electrons between the two half reactions. It is number of electrons transferred. Least common multiple between the two half reactions. So as we learned last week, how to balance redox reactions, we adjust the coefficient of the two half reactions so that the number of electrons given by the oxidation reaction equals the number of electrons taken by the reduction reaction. So that's the N, it is number of electrons transferred. There's another way to find out the number of electrons transferred. It is use the change in the oxygen state. And also we consider how many atoms undergo such a change. So the number of atoms times the number of electron transfer per atom, we get the number of electrons transferred, which is the N. So how to do that? And let's see, there are two examples. I give two examples here. So the use oxygen state change to find out the electron transfer. We need to be very familiar with finding oxygen states for each element in the balanced equation. So let's quickly go through together the iodide. You can see this is I minus. The I minus oxygen number for the iodine is the charge, which is -1. Hydrogen, same as the monatomic ion, so it's +1 for the hydrogen. And then dichromate. Dichromate, we start with oxygen. Okay, as we review this together. Start with the oxygens, -2, and then do a little math, find out oxygen number for each chromium. The chromium finally will end up is +6. And here the I2 is the element, so 0. And also the charge, you can see this charge, 2 iodine have 0 charge. So each iodine is 0 charge. And then water. Water, this we start from hydrogen. And because hydrogen plus 1, then the oxygen will be -2. And last one is also monatomic ion. So the oxidation number, it is +3. So to use oxidation state to find out electron transfer, we need to find the oxidation state for each element first. And then next, we look at the how each element change. And let's first take a look, find out which element did not change. The data will get them out of the picture. Will make the picture much simplified. You can see the hydrogen +1, and in the end also +1. The hydrogen, no change. We don't need to consider hydrogen. We don't need to consider hydrogen. And same as oxygen. They are -2, so we don't consider oxygen. And now we can have a much easier to see the iodine. Iodine start from -1, become 0 for each one iodine. So the iodine, what we see is from -1 becomes 0. So I have a question for you guys. What happened to iodide? Does it lose or gain electrons? Does iodide lose or gain electron?
Lose?
Because, correct. Because the oxygen number increases from -1 becomes 0, increases, and the electron is negative charge. And so if the charge increases, that means it lost the negative charge electrons. Each iodine lose 1 electron per iodine atom. It loses 1 electron per 1 iodine atom. And now you have a 6 iodide in this reaction. So the total number of electrons lost by the iodide is 1 per atom times 6. This is the number of electrons transferred in this reaction, which is the N. So it's pretty straightforward to find out number of electrons transferred if you can work out fairly quickly the oxidation states for each element and watch how each element change. The oxidation state or oxidation number increase means loss electrons. If the oxidation number decrease means the gain electrons. So this is, we look at the iodine, we find out the number of electrons in. We can use the chromium, because we notice chromium also changes. So if you look at chromium, this is the alternative. You don't need to do both, because if your equation balanced correctly, and you find out the number of electron transfer from one element correctly, you don't need to do both, but just for more practice. If you look at the chromium here, each chromium, this is the chromium oxidation numbers +6. And you look at the product, chromium becomes +3, so chromium decreases. Chromium decrease, that's a gain electrons. And the chromium from +6 become +3, it decreases by 3, which means gained 3 electrons per 1 chromium atom. 1 chromium gain 3 electrons per atom. And in this balanced equation, there are 2 chromium. So the number of electrons transferred, it is 2 times 3. That should give me the same. It should be the same number as I get from the iodine. And so this is how we determine number of electrons transferred. Once you find the N, the rest should be fairly straightforward to calculate the free energy change. Just use N, negative N times Faraday's constant times the cell potential you calculate with the cathode potential minus anode potential, or reduction potential minus oxidation potential to calculate that. You get a free energy change. And so that's the, we find the oxidation state change. So this second one is very similar, and now I do much quicker. So with the manganese, it's the oxygen -2, and if oxygen -2, then the manganese is +7. And here, this is the oxalate ion, oxygen -2. Carbon, this is actually will take some time to figure out because we add together, give you charge -2. This carbon should be +3. Okay, I did this a long time ago, so it's fairly easy for me to recall that, but you should take some practice, take some time to figure this out. The hydroxide, oxygen is -2. We actually start from hydrogen, hydrogen +1. And manganese 4 oxide, so obviously that already tells you what the oxygen number. The Roman number is the oxidate number, or oxygen state, or oxidation number. Oxygen -2, and here oxygen -2, carbon +4. And the last one, hydrogen +1, oxygen -2. All right, so with this, same thing, we notice oxygen don't change, hydrogen don't change. Now we only look at the element that changes oxygen state from the beginning, from the reactant to the product. So this is the manganese start from, okay, let's look at manganese. Manganese start from +7, it becomes +4. So the question is, does manganese gain or lose electron, and how many per atom? Can anyone answer that? Tell me this. How many electrons manganese gain or lose? From +7 becomes +4.
Lost 3 electrons. Wait.
It's gain. You can see the oxygen number decreases. Oxygen number decrease is gain electrons. Decrease number means by adding negative charge, by negative values. We add -3 to the +7, give me +4. We add -3 to the +7, give me +4. So it gains 3 electrons per atom. The oxidation state or oxidation number decrease, it means gain electrons, which is also oxidation. This one decrease, so it is gain electrons and the reduction. This is a reduction. The changes from a high number to low number, it means a decrease, means a reduction. So the reduction, actually the reduction from the origination, it is based on losing oxygen or reduce in the charge or oxidation number. That's where the reduction words come from. Reduction means lose oxygen. And oxidation means gain oxygen or increase in the oxidation number. And so that's basically the manganese gains 3 electrons per atom, and there are 2 manganese. So the number of electrons, it is 2, because there are 2 manganese atoms, and each manganese gains 3. So for this half reaction, manganese also gained 6 electrons, which is number of electrons transferred. What happened where does electron come from? Manganese take those 6 electrons. This electron should come from the carbon. And you can see the carbon. The carbon oxidation number start from +3 and becomes plus 4. So the carbon oxidation number or oxidation state increased by 1, which means it loses 1 electron per atom. It increased by 1, which means it loses 1 electron per atom. And how many electrons totally lost by the carbon? It is number of carbon atoms. Okay, look at the equation. There are 3 oxalate ions, and each oxalate have 2 carbons, so the total number of carbons is 6. Each carbon loses 1 electron. So this also gives me 6. So either way, with this reaction, by using the oxidation number change and count how many number of atoms involved, we can find the number of electrons transferred in this reaction. And these 2 reactions, it so happens the number of electrons both equal 6. But these 2 are completely different reactions. And so that's how we find out the number of electrons transferred. Either this way or you balance the half reaction. And when you balance half reaction before you combine together, to make the 2 half reaction have the same number of electrons, we turn number of electrons to the least common multiple. That least common multiple is the number of electrons transferred in the reaction, which is the N here. So that's how you use N. All right, so let's see an example here. This is the, in the industry, it's a chemical process we use in the industry. Lead is fairly cheap metal because they are in a much bigger quantity in nature. But the lead and silver, because both react with the sulfur and form very stable compound. And the lead in nature oftentimes appears as a sulfide. So when the human do the mining of the lead from the sulfide compound, goes through the combustion and some reduction to produce lead metal, we can also get a tiny amount of silver. And between the 2 metals, lead is chemically more reactive than silver. So in the industry, when we do the mining of the lead, there's a tiny amount of silver that we can recover. The way to recover that is we put the lead compound, which contains a tiny amount of silver, and dissolve in the as a nitrate compound, which is soluble. And towards this soluble nitrate solution, which containing the lead and silver ions, we add the lead metal. Consider the lead metal is much more inexpensive. We use the lead metal to react with silver ion. And the silver ion will be reduced into silver metal. And so this is one way to recover, to recycle the trace amount of a small amount of silver from the lead mining process. And by the way, lead is a fairly inexpensive metal and used in the industry since ancient times. Ancient Rome actually used the lead metal to make the pipe for their water supply system. So that's where the word come from. Plumbing, it is the word plumbum, which is the PB come from. The word PB for lead is come from the ancient Rome. Plumbing, use the lead for the pipe. Anyway, this is the reaction we have. And this reaction is a single displacement reaction. This reaction to calculate equilibrium constant and free energy change, and we were given the standard cell reduction potential for both half reactions. So to do that, this is a very good exercise to practice on the free energy change, the cell potential calculations. To do this, look at the first reaction. This reaction, we need to break down to two half reactions. Break down two half reactions. That way we will know which element is being reduced, which means oxide, and how would we calculate the cell potential. So the half reactions start from this. Lead becomes lead ion. So lead metal becomes lead ion. And the other half is silver becomes a silver metal. Silver ion becomes silver metal. And by checking the change in the oxidation state, this is the lead 0 element. And this is lead ion +2, same as charge. So you can see the lead oxygen number increases. So this lead, it has been oxidized. It's oxidation half reaction. And the silver oxidation number start from +1, become element 0. So you can see the decrease. That's the reduction. The cell potential for this reaction, we can calculate use the reduction half, which is the silver, minus oxidation half, the cell potential. The reduction half, we just decided silver because the electrons lost, gained by the silver. Silver is going through reduction reaction. And the oxidation half is lead. And now we can just substitute those symbols with value. The silver is positive 0.80 volts. And minus lead. The lead reduction potential is -0.13. So it's a simple calculation, simple math. You can see this reaction have a positive standard cell potential, which means the reaction is spontaneous. And that's why we can use lead to reduce silver ion, become silver metal. So that's this. And to calculate K and delta G, we have those equations in the last slide. Let's do the delta G first, because that's actually the equation is much easier to this is how we calculate free energy change. And the N, what is N in this reaction? So N in this reaction, we'll look back as this balance equation. And let's mark the oxygen state for each one. The lead start from 0, silver is +1, lead becomes +2, and silver end up with 0 because element. You can see there's only one lead atoms, and each one lead lost 2 electrons. Each lead loses 2 electrons, and there's only one lead. So the number of electrons transferred, it is 2. 1 times 2, it is 2. The N equals 2 for this reaction. Times Faraday's constant. The Faraday's constant you can copy from the constant given for the units. Okay. Actually there's 2. We should add mole. The unit for 2 is actually 2 mole. And the Faraday constant is the joule per volt per mole. That's a unit for Faraday's constant. And times the cell potential is a positive 93 volts. So the rest is fairly straightforward math. And we should keep only 2 sig figs because cell potential. The n is exact number. It's so infinite sig figs. Final answer, keep only 2 sig figs. And the units should be in joule because all the others got canceled. 2 sig figs for the free energy change. And it's a negative value. Don't forget that. If it's positive, then the reaction will not be spontaneous. It will not take place, literally. So that's the free energy change. And the K, to find a K, we need to use the knowledge from last chapter. That'll actually make it a little bit easier because delta G is equals negative RT natural log K. So the K with this equation, this comes from last week. Free energy change and the equilibrium constant equation. From this equation, and make sure you plug in the delta G as a joule. Oftentimes, the energy discussed in chemistry, when you calculate, oftentimes we're given as kilojoule. When you use this equation, make sure you use joule to divide by R and divide by the absolute temperature, Kelvin temperature. And the final answer, the sig figs depends on how many decimal places in your exponent. And that should give us the final answer. So that's the K for this reaction that we calculate. Any questions? And so the voltage, the cell potential, by the way, we can measure with a multimeter. And the cell potential we measured, if it's a standard cell potential, it is supposed to be under the standard condition, where the solution of the ion should be maintained as 1 molar, exactly 1 molar, 1 mole per liter. And if a gas involved, the gas partial pressure should be equal to 1 atmosphere. And also, when you measure the standard cell potential, there should be no load, which means electrons are literally not moving. It is just have the potential, but not moving. What really happens is as you use the battery, as you're running the battery, the actual voltage will be low, what is it said. And the most battery, okay, the fresh battery start, the alkaline battery start 1.6 volts. And as we all know that, just like our cell phone batteries, alkaline battery also, the voltage will decrease. Over time, it will decrease to about 1.2 volts, then it will stop working. It's no longer good for to push electrons to do any electric work. So there's a voltage decrease as we use. Why? We have another equation that explains why there's a voltage decrease. It is because the actual cell voltage, it is a standard cell voltage, subtract a term that is depending on the reaction quotient. So as most chemical reaction progress, there will be more product being produced, less reactant remain in the system. And as a quotient, it is basically the product. A simplified version for the quotient is basically the product over reactant. As the reaction progresses, there will be increase in the product and decrease in the reactant, so the quotient will increase as the reaction progresses. Increase in the reaction quotient, it'll cause this portion become more and more negative. So the overall cell potential will decrease in the end. And this equation we call Nernst equation. Is the physicist Nernst established this equation. And it's pretty straightforward. When the quotient less than one, that means you have more reactant than product. And so the actual cell potential will be higher than the standard cell potential. Quotient equals 1, by the way, standard condition, this if all the reactant and product have the concentration or pressure as a standard state, which means 1 molar, 1 atmosphere, then the quotient will equals 1. And then when the quotient equals 1, these two will equal. Because when all the molarity equals 1 molar per liter, or pressure as 1 atmosphere, the quotient is 1, and that is a standard states. So they will equal. If the product is more than reactant, you have quotient less than 1, the cell potential less than the standard cell potential. This is where explain why any batteries that we're using, the longer that we use, the voltage will decrease more, because the longer as we use, the more reactant will be consumed. Less reactant available, more product being produced, quotient will increase, the cell potential decrease. And this equation, we use the room temperature and the log of 10. You have a number for this. This number comes from the R and T, RT. And there's no factor in there's a ratio between natural log and log of 10. Natural log value for the same number, natural log will be 2.3 times bigger than the log of 10. So all these combined together give us a number 0.0592. Okay, so the N is number electron transfer, just as we discussed earlier. Okay, so this is a little practice. And this example is one of the harder, more difficult. And in our quiz, we have similar questions. So we have this is a reaction. We want to calculate the actual cell potential. And we have 2 conditions. This is the combined overall reaction. And we were given the concentration of ions for each. For protons, proton concentration is not given, but we were given the pH. Or given pH. So we'll be using this Nernst equation to predict if this reaction have the forward reaction spontaneous, or the equilibrium shift to right by using the non-standard free energy change. So we have the ion concentration, and we have pH, which means proton concentration can be derived from this pH. And we have actual reaction 6 chloride with 14 protons, and with dichromate give us the chlorine gas, and water, chromium-3 ions as product. And when the cell potential, when the non-standard cell potential, as opposed to the standard cell potential. The standard cell potential is predict if the reaction is spontaneous. The non-standard, it is predict how the equilibrium will shift. Will this system, from the beginning, will the shift to left or right? It is use the actual cell potential calculated by the Nernst equation. As we can see, from the Nernst equation, the quotient can influence the cell potential, which means the quotient can affect how does the redox reaction equilibrium will shift to right or shift to left, just like we predict from the last chapter when we discussed non-standard free energy change. So likewise, in this chapter, we can use the non-standard cell potential to predict. And so for this reaction, we have the 2 half reactions. So when you solve this problem, you need to find the standard cell potential first. This is the first step. Find what is the actual standard cell potential. So that means you start from this reaction, you need to break down as 2 half reactions. And with 2 half reactions, you will know which one is reduction half and what's the oxidation half by observing the change in oxidation numbers. Okay. Use a half a reaction. Find the oxidation state for each element, and then you will know reduction half versus oxidation half. And then once you know this, you can calculate based on the standard reduction potential of these two. Find the cell potential. Okay, so that's the first step. Find the cell potential. Step 2. Nernst equation, the actual cell potential depends on the reaction quotient. And the reaction quotient, QP, for this reaction, if you look at the balanced equation, you have a chlorine gas, water liquid, chromium-3 ion as a product. So each of those products, the concentration or partial pressure of gas raised to the power of the coefficient. Okay, so those are the products. You have a whole bunch of products divided by the reactant. And your reactant has a chloride ion, proton, and dichromate ions, each one of them are the reactant. Concentration raised to the power of the coefficient. So that way you find the reaction quotient. And then once you find both the standard cell potential and then the reaction quotient, you can do the final combining that together. The Nernst equation to solve the actual cell potential. Okay, so I'll break out do the breakout room. And I'll let you guys discuss how to work on this problem. Okay, so let's first, A, the H plus will be, since this is 1 decimal, the concentration of protons should be 1 sig figs, and quotient. This is quotient of QP, so use the pressure, partial pressure to calculate. The room 1, can you share with me your quotient number? What's the quotient you get? Keep it 2 sig figs. I underline we should keep only 1 sig figs. What's the QP you get from room 1? Yeah. Anyone two notes? Your room 1?
2.2 times 10 to the 88th, I thought it was.
Yes, it is a very large number. Everyone agree that's 2.2? I'm not sure what the, let's just put down here.
I got 2.6.
Yeah, sounds like different. There's someone different numbers. But we are supposed to keep only 1 sig fig, so the 2 will be kept. And 2.5, 2.2, 2.6, I don't know which one to pick. Okay. But anyway, the natural log of the quotient QP, you get a, you should only have 1 decimals, okay, with a QP. QP only 1 decimals. 1 decimals. I think you should get about 20 or 30 natural log QP. I think most of you did not really single out the calculate quotient. But anyway, your final, the cell potential, you get a negative 0.93. Let's assume your sig fig is right. Keep only 2 decimals. That's what you get. So with the first neutral condition, when the pH is neutral, this reaction is even less favorable for the forward reaction. It's definitely not spontaneous for the forward reaction, or the equilibrium will not shift to the right. Okay. At the equilibrium, at the neutral condition, the actual potential is even more negative. It will favor more to the reactant. And with the condition B, it's actually 0, sorry, which I don't need to put in there. But the concentration of hydroniums is a big number. And your quotient, how about the room 2? The room 2, can you share your quotient you get?
It's 3 times 10 to the negative 17.
17 is a very small number, which is good. Small quotient is favorable for the product. It will equilibrium shift right. So 3, we should keep 1 more, but the 3 is the one we should keep. Add 1 more for calculation in the middle. Okay, so.
Oh, did you want 2 sig figs?
Yeah, if you keep 1 more digit, it'd be better.
And then it's 2.6 times 10 to the negative 17.
2.6?
Yes.
6. Yeah, we're supposed to keep only 1 sig figs. And then this actual cell potential, what you get is a positive, right? Did you get all positive numbers?
We got, yeah, it's 0.4.
Keep 2 decimals.
Okay, 0.37 then.
Yeah, 37. Okay. So you can see the pH make a big difference in the direction of this reaction. Under standard condition, when you calculate the standard cell potential, so this is reaction, standard cell potential, negative 0.03 volts, almost 0. If the cell potential is 0 means the reaction equilibrium. There will be no, or the equilibrium constant K equals 1. But this number is very close to 0, slightly negative. That means this reaction slightly favor reactant. And by adjusting the pH, and you can see when the pH is very high, pH high, that means your hydrogen concentration ion is very small. And as a reactant, low concentration reactant is actually not favorable for the forward reaction, according to the Le Chatelier's principle. And so it makes sense. So final calculated quotient is very large and cell potential is very negative, which means favor the reactant. For this reaction, at the high pH, the reaction will shift to the left. Reactant will shift to left because of low concentration reactant. And condition B is when you have a low pH, is negative pH. Negative pH is the hydrogen concentration more than 1 molar. It's actually 3 molar. 3.2, I think, 3.2. You keep only 1 sig figs. So 3 molar high concentration reactant, if it pushes the reaction to the right, and you can see the actual cell potential actually become positive. That means for this reaction mixture, it will progress to the further right to produce more product and do more work. And so that's, you can see the Nernst equation affect the reaction quotient, the actual cell potential. And it helps predict how this equilibrium will shift to right or left. So let's take a break. Okay, so the reaction quotient affect the cell potential as we calculated with example and practice. Also, we can see for a simple reaction that like a copper zinc cell. This is the cell we started in our lecture. And the quotient, because the reaction is the zinc. And so the quotient for this reaction is the concentration product over concentration of the reactant. The solid concentration treated as a constant, which is 1. So that's what quotient looks like. So as the reaction progresses, the actual cell potential, which is the Y, it actually decreases as the natural log of the quotient increases. And so that's cell potential. The cell potential eventually will become 0. That is when the quotient equals K. When the quotient equals K, the actual cell potential equals 0. And the concentration cell is very unique. It is basically the same, both have reactions. It looks like the same. Both have the same components. The difference is one half cell have a different concentration than the other cell. And when the concentration is different, it will cause the actual cell potential does not equal 0. So here's the example. We have both solutions are copper metal with copper ion solution. But one solution is more concentrated. The copper ion concentration is 1.0 molar. The other half concentration for the copper ion is 0.1, so it's more diluted. And because the concentration difference, between these two half cells, the voltage actually is not 0, even though they are the same kind of cell. And because the standard cell potential, it equals 0, just because they're the same cell. The quotient, however, the quotient does not equal 1. does not equals 1. Which means the actual cell potential is not 0. And the results is because cell potential is not 0, there's net reaction between these two. So we start with the one side is diluted, the other side is more concentrated. And the net reaction, because the cell potential actually is not 0, there will be net reactions. The diluted solution will give more electrons. And those copper ions becomes increasing. The copper ion concentration will increase. And those electrons will given to the concentrated solution. And here, because the copper ion gains electrons, the solution concentration will decrease. The concentration, this will decrease. And the dilute concentration will increase. The other effect is that since copper becomes copper ions, this copper will be corroded, will lose copper. Copper will decrease. The solid will decrease. And on the other side, the right-hand side, electrons coming in, it will reduce the copper ion to copper metal, which accumulate on the copper. The amount of copper in this concentrated solution will increase. So over time, there's a change in the between two half cells, even though they are the same cell. Standard cell potential equals 0. There's net reaction because concentration difference. Concentration cell voltage, it can be easily predicted by the Nernst equation. The concentration cell or cell voltage affected by the concentration, we can use to measure the concentration by measure the voltage change. And actually the pH meter, it is based on this principle. And so the exact working principle, I will not give you too much detail because we have a reference electrode, we have an electrode that is a voltage depends on pH. And so as the pH changes, the voltage on the on one of them will change. And on this one will change. As a voltage change, it can be translated into the pH. And there are many other ions we use as electrochemical. And the electrochemistry is very good detecting low concentration ions as you find the proper electrode. Batteries. The battery is a big category. I will spend not too much time on discussing. Just briefly introduce what is the reaction and start from the basic alkaline batteries. This is the most ancient battery. It's pretty much started from 200 years ago. You use the same principle as this. And the zinc is a common anode material because zinc is a very inexpensive, chemically fairly reactive, very good reducing agent. So zinc is commonly used for the anode for those batteries. And silver battery have used different reactions, use a silver oxide reaction. The silver oxide is the oxidizing agent. Again, the zinc, it is a reducing agent. And the lead acid battery use a reaction that is use lead as anode. And the other cathode is lead-4 oxide. This reaction is rechargeable. Can be easily reversed. The lead acid battery has been used in our car for almost 100 years. And it's very reliable. It's very heavy because lead, but extremely reliable for 10 years. And they won't catch fire like lithium-ion battery. And the only thing, the lead acid battery, it needs to be maintained fully charged. And that's very different from most batteries. And so if you leave your vehicle, the headlight is on, or somehow the engine was not completely turned off, it'll drain the lead acid battery. It can be damaging for the longevity of the battery. It shortens the life cycle. So you need to maintain fully charged. Can record late. And that's the last part of the chapter.